program, so let's start. Welcome everyone to this edition of Verifiability Talks. It's my honor and pleasure to introduce Yiannis Demiris, who is a professor of human-centered robotics. I hope I got that right, at Imperial College. He has done a lot of very, very interesting work, which has a lot of overlap with what we are trying to do at the Verifiability Talk, Verifiability Node. And without any further ado, I give the floor to Yiannis. Thank you very much, Yiannis, for having accepted the invitation. This meeting is being recorded. We will record it up to the point where this discussion starts, and hence you may appear in the recorded version later on. So if you don't want your name, for example, to appear, you could join as a guest, for example. That's one way of avoiding that if you're unhappy with being shown on YouTube. Thank you very much, Yiannis. The floor is yours.
Great. Thank you for the introduction, Mohammed. It's a pleasure to be here. Let's see whether everything will go well. You guys see me full screen?
Yes,
perfect. Great. Okay, thanks again for the introduction. You know, I'm happy to see that I know a lot of people already in the audience, and I'm looking forward to our discussion so I can meet even more. So today I will talk to you a little bit about my research on personal assistive robotics. This is very kindly supported by the Royal Academy of Engineering through a chair in emergent technologies, and the goal over the next whatever is remaining now 8 years is to see whether we can build robots that can help us in an intelligent way to achieve our task, right? So that's basically my overall goal. And what I will describe later is that I believe this personalization is a key aspect. So it's not only that the robot helps you, but the robot can build a model of you and then adjust the assistance to help you in an optimal way. Today I will actually talk with two different hats, right? So I will talk about my research in my lab, but also as a representative of the node on trust, you know, a sister node to the verifiability node. So you guys probably, you all know that we have 6 nodes or 7 nodes on different aspects of trust. Ours is a little bit on essentially maybe the more human side of things. So we are very much interested in seeing how we can create cognitive architectures for trust, modeling different trust factors, quite a lot from the human perspective. A quick introduction, Helen Hasty is the coordinator of the node up in Heriot-Watt, has expertise in human-robot interaction and linguistics. Tushar Rajendran is also in Heriot-Watt since he's from the psychology department, and he has a very nice expertise in developmental science. And these guys are from Heriot-Watt University, and we are joined by Angelo Cangelosi with a cognitive science and psychology background in the University of Manchester, and myself down at Imperial, mostly on the robotics and ML side. So the kind of the emphasis on the trust, and the reason I'm giving you the overview, because it would be nice if we see we can collaborate between nodes, of course, is essentially, can we create the cognitive architectures to model different aspects of trust, how it develops in humans, how it changes, but also how can we define a set of principles of how trust is acquired over time, because we believe it's a dynamic concept, how it's adapted to the context that the interaction is taking place in. What happens if the humans or the robots make errors? How do we adapt to different environments, different users, and how basically we can adapt all the systems differently? And at the end, also, can we create an evaluation framework so we can actually reliably measure trust, right? So the idea is maybe we can do this applicably across multiple applications, and also with varying user proximity. I will come back in this in a minute. My goal in my particular task in this node is mostly on this part. So how does trust is acquired and adapted and in a way personalized? The reason we say about varying user proximity is because actually we have quite a lot of robots. So across the three sides, I think we probably have most of the robots that exist. So we can actually do experiments in many different situations. So either in hazardous environments or in this is here, or in kind of cobot situations or healthcare and rehabilitation. And the idea is that not only we do it ourselves, but maybe we're going to try to do it together with other nodes. And you can see here different types of kind of collaboration opportunities we have listed. So, for example, you know, we would like to collaborate with people on the modeling side. You know, how can we represent the acquisition and development of trust using a cognitive architecture? How can we build methods of adaptation? How can we have an evaluation framework that is shared? Can we build some use cases that involve human in the loop? And can we possibly, or impossible, is coming up with some kind of common definitions? I'm not very convinced about that, but we'll see how it goes. And of course, some kind of experimental protocols. The main part that I work is this part, the healthcare and rehabilitation. And the majority of the work I will present later from my lab is focusing on that part, right, on the healthcare part. And what I'll show you in a little bit, I don't mean surgical robotics or aspects like that. It's more interactive aspects of healthcare. So this is basically kind of an overview of the node. I can come back later and describe more about the node if anybody's interested to discuss more. But let me walk back and to my own research in my own lab. So we call it personal robotics laboratory because we actually want to build cognitive architectures to have robots that can personalize the assistance to humans in many different environments. So let me give you a couple of examples. On the top left, here you see some of the work that we did. This is probably the work I like the most, I guess, on building robotic wheelchairs, smart wheelchairs for kids with disabilities. And the idea is that if you build a wheelchair that enables children to explore the environment, then we enable better development of their sense for motor skills as well as the cognitive skills, right? Because they can actually play like other kids do. I'll come back to this example later. On the right-hand side on this video, you will see some experiments we did with taking some small humanoid robots here as the now into our local hospital, the Chelsea and Westminster Hospital. And we took it in the intensive care unit and tried to see whether we can build some sort of demonstrators to show different rehabilitation exercises to people that just underwent surgery, not to replace doctors or nurses, but to supplement their, because they have a lot of other demands as well. So they go there, they show some exercises, and the patients do more of those, right? There wouldn't be enough people to do it constantly. On the third video here, it's another type of assistance. So here, for example, the robot sees and models how the humans move, this particular human moves, and then it adjusts the assistance to match the difficulties that this person is facing to make the whole interaction more comfortable for this person. So the idea here is the robot doesn't do the same sequence for every person, but it changes depending on the difficulties that this person has, right? The motor difficulties. And finally, on the bottom right, I think the video has stopped, but we also did more kind of like creative aspects. So here's the iCab robot is actually playing with a human on a musical touch surface, trying to perform a joint musical performance. I think that it's a small sample of the kind of task we do in the lab. As you will see, we focus quite a lot on this idea of real robots, real environments, real humans, right? So we want very much to see how far can we actually go with actually assisting humans in real environments. Some of these, for example, this experiment here, and of course this experiment up here as well. Some of these, you can imagine, trust is a core requirement, right, for these applications. I mean, if you are going to be in a machine that's going to move you around, or if you're going to be with a big robot behind you trying to help you dress, you must really trust these systems that they're not going to do damage on you, right? So I think that you can see how we can have a huge interest in building trustworthy systems. How do we do this? Well, I try very much to encourage my students to follow an approach where we build an architecture that can work in many domains, right? We don't want to build something hacked just for a particular application. So we try to build an assistive cognitive architecture that senses the user states, models the skills, and tries to predict the intentions of the users, and then personalizing the assistant. So first of all, you have the human there doing his task, a kid there. And as it's moving along, we perceive all the user states, right? So everything that the kid is doing through the multimodal interface. So eye tracking, head movements, joystick movements, haptic information we might have, any kind of information we have from the kid, we feed it in our systems. We use machine learning to actually build some kind of user models that change over time to model the change that the child itself is going through. And trying to see whether we can actually predict intentions later. And once we can actually build a relatively good user model, we actually adapt the robot behavior to improve the interaction and the assistant effectiveness. So we actually we don't provide the same assistance all the time, but we change it to map what we think that the child needs over time. So I think the key challenges for us are these ones here. So first of all, how we are supposed to help and when we are supposed to help. So this implies that we can understand the user's intentions, what is the person is trying to achieve, that we know their capabilities, what can they achieve with the current skill set. Then we have to determine whether we can help, because there are cases that you cannot help. And finally, we should think about whether we should help. Many times, especially when we're helping kids, we have to think developmentally. So, many of you are parents, and you're not supposed to help your kids all the time. You're supposed to let them do some things by themselves. So the idea is that help is not always wanted or needed. So we have to find out when is the good time to help. For doing that, we've been working quite a lot on this idea of theory of mind, basically trying to see how can we get into in quotes, the mind of the person we are observing, and trying to understand the human state, the states, underlying the sensory data we're perceiving, and what is the person trying to achieve. We do this using this architecture that we've been working for quite a few years now. This idea that we actually have multiple models that work in many different levels of abstractions to internally generate what you observe. So I will go this into detail in a minute, but essentially we trying to reproduce internally in our internal systems what we observe externally to understand it better. And as I said, we're trying to do this in many different cases, from kids with disabilities, interactive robots, or robots that actually help you to get dressed. Here is the kind of pipeline that we're trying to build. So starting from the top left. So essentially we have a person. The person might be freely moving or might be on a wheelchair. But in any case, it doesn't matter the conditions that they're at. We try to track a little bit what is their, through multimodal sensory interfaces. We're trying to track the state. So getting the information in will, through images. The two things we're trying to do is, first of all, see whether we can understand the body structure, the articulations they might have. And the reason for that is that is not always the same with everybody. People come in different sizes and capabilities, and we actually try to understand what is the kind of articulation structure of the person that we're observing through videos. So basically by observing them. And at the same time, we also do eye gaze tracking to see where this person is looking at. Once we have the articulation of the person we're observing, basically the kinematic system, we're actually trying to see, can we match what we're observing to a known structure? So we do this what we call articulated structure matching, where the observed articulation is matched against known models, right? So, and in that way, you can actually put into the model any knowledge you might have about, for example, people's pathologies, and etc. Once you have a kind of a relevant model you can map it to, one thing you can do is actually start learning about the movement. How does this person move? Start collecting data about this person to try to understand how does this person changes and is different from the models you know so far, and try to basically to see whether we can learn movement properties. For this part, we use sub-symbolic action representation. So I will show you in a little bit. We do things like statistical machine learning or neural networks, etc., because they deal better with things like noise essentially with noise. At the same time, of course, people don't only just move, they act in the environment, and we also want to learn about how they solve problems, because that sometimes gives you an indication about their internal state. And for this, we use kind of symbolic action representation. So I will speak a little bit about the kind of grammars aspects we work with, and possibly this is also some way that connects our work with the work that you guys do in verifiability, because you can probably work a little bit in these aspects of proving properties about what you're observing. Now, all these things here are done constantly, and eventually we end up with a model of how this skill set of the persons is actually changes over time, right? Because either you're learning and you're getting better, or if you're elderly or after an accident, you are actually getting worse. And therefore, it will be nice for us to know how is your skill set changing over time. And this kind of like pipeline is working constantly, keeping a constant monitoring of the person and trying to see whether you can learn a model and learn how it changes over time. Now, let's say that you have a model, right? So you build a model of how this person is changing, what is the skill set and how it's changing, and you have a robot that it can do something, right? So this is the kind of the input to the assistance systems, and then you can have different aspects you can actually model, right, and do. First of all, you can change the way you help. You can change the level of autonomy, right? So for example, you can intervene much more if you think that the kid is in danger, or if you think that the person cannot dress themselves and you want to help them a bit more. But essentially, the first thing you can do is change the robot's behavior in how much does it help, right? So this is the first type of assistance we can give. Another thing we can actually change is that if you're providing examples, like in intelligent tutoring systems, you can actually provide different levels of training difficulty. So in this is some of the work we did for a European project called Alize with a bunch of hospitals as well. So this is an Italian hospital in Milan where we change the exercises we're showing to the kids to match how well they're doing this exercise. So nobody gets the same training programs based on the errors you make. There is a camera below the desk to analyze the movements of the kid. The now is actually recommending different exercises. And apart from that, you can actually even modulate, in order to assist, you can modulate how you present the information that the person needs. So in some of the work we did more recently, we have been doing, we're using augmented reality to change the information that the person is getting to understand a little bit more about how is the robot is trying to help them. This is essentially a broad overview of the methodology, right, at a high level of what we're trying to achieve. Now, how do we do it, right? Let's go a little bit more into detail. As I said, I'm trying to do this through a kind of a unified architecture. Of course, this is a kind of a ongoing saga, right? We are nowhere close to having one thing that works as a black box for everything. But this is kind of like a goal to see how far can we actually go with a unified architecture. So we call it HAMMER, for Hierarchical Attentive Models for Execution and Recognition, rather long title. But essentially what it is a kind of an ensemble architecture, right? I like very much things that work in parallel and in uniform, so I like quite a bit of diversity and kind of things that work together and compete with each other and to do something that one model cannot do by itself. So this is essentially several learning algorithms that are working concurrently at multiple levels of abstractions, and I will explain more about that later. But essentially, they constantly trying to learn things about the user, right? How they look, for example, the user's morphology. How does the user move? And this is the learning I was telling you about the trajectory level. And we use a lot of stuff there: Gaussian processes, quantum mixtures, echo-state neural networks. It doesn't really matter for this talk what exactly we use, but we use a kind of ensembles, many different machine learning modules for achieving this, the learning at the trajectory level. But also, as I said, we're trying to see whether we can solve problems. How does the people solve problems? And this, as I said, we're using context-free grammars for these aspects. But also, how do they change over time? So we're using this, we call it autobiographical or heterobiographical memories for long-term interaction. So the idea is that as you interact with a robot, it keeps remembering what you did, and it's trying to personalize the assistance to make it more effective for you specifically. How does it work? Well, I come from a bit more AI, and kind of control kind of background. So we use the same blocks, even if the kind of routines within that change, the blocks are remain the same. And these are essentially either forward models or predictors, or anything you want to call them, where essentially you give the current state of the system you're observing and an action, and that gives you a prediction for the next day, right? So it's a really crystal ball that tells you if you do this and you are in this state, this is what's going to happen next. And the other way around, we also have an inverse model that if you give the current state and the target, where do you want to go, it will tell you how to do this, right? So this is an action that comes out. Now, these things essentially sometimes we change what is contained in different ones for different situations, or we use ensembles of these, but the building block remain the same because we want the whole system to be modular. How do we make it work? So if you have a robot or you're modeling a human and you want to basically execute an action, essentially you just have a pair of inverse models, right? So it's a current state, it's get fed in an inverse model, then this model tells you, what action you should do. You send it to your muscles or models or motors or whatever you have, and you get back some feedback through proprioception or vision or any other stuff you might have. Now, the idea here, of course, is that if you try to do this with real systems, you have delayed feedback, so you don't get the feedback straight away. And those of you guys that have done control theory, you know that control with delayed feedback is challenging. So what we usually do is we put a forward model and a little internal playground, let's say, a little predictor that gets a copy of the action and gives you a prediction of the next state before you actually get it from your sensor itself, right? So you have a bit of chance to inject some corrective signals if you predict that the current action is not going to give you the result. And of course, if you actually inhibit the signals from being sent to your muscles or your motors, essentially you can do with this loop here, you can essentially do internal simulation, right? You can actually simulate the system internally before you actually do an action externally. So essentially, in quotes, mental rehearsal. Now, this was if you know what you want to do, right? If you want to plan what you want to do and you don't really know what is available, how would you do that? The way we do it is in a distributed manner. We take the current state, where are we now? What is the target we want to achieve? And we send this to all our inverse models. So I have a bunch of ways, plans, controllers, behaviors, anything you want to call it. But essentially, these are models that tell you that if you wanted to go from this current state to this target goal, this is what I suggest. So each model would give their own suggestions, right? Now, you don't believe any of them, and you say, let me pass them all through my forward models. And each one of them gets evaluated and gives you a prediction of the next state. So if I follow this action, what would be the prediction for the next state? And we do this in parallel with all the models we have. These states are actually compared against the target goal. And of course, the models that predict well and get you closer to the target goal will get some better confidence. The ones that do not will get some corrective signals and have their confidence lowered, right? And this happens in parallel. And you can have a lot of different types of models for different blocks that you have there. Now, the key point here is that we can actually use the same architecture that the robot is using for itself, for its own planning and for its own execution. And you can put, bounds in how all these things can happen. You can use it also to understand other people and the other agents in the environment. So if you use the same planning systems, so instead of actually feeding in your own state, you feed in the state of what you observe from the user, from your partner. You feed all these inverse models, you're getting a prediction, a set of suggestions of what you could do if you were in the shoes of that user. Then you put it through the forward models and you get a prediction of the next state, right? You feed this into the actual state that you observe from the users, and you get back again some corrective signals. So essentially, you internally simulate with your own systems what you see the user doing on the outside, right, from your cameras. But very importantly here, you don't wait until the whole thing finishes, right? This is the important thing. So I give you some examples now from simulation here. So this is, for example, a person like throwing a ball. And you can see here from the evolution of the confidence that we don't wait until the whole thing finishes before we classify what happened and potentially give some assistance. Anything that's happening, even whether it's a kind of like facial expressions and you see different expressions might happen, or throwing a ball or moving it, any of the stuff that's going on in the screen, I would like to give you the understanding that we don't just collect data, classify, and then respond. For human robot interaction and for assistive tasks in real time, you need to be able to predict what the user needs before the sensor data tells you so, right? So you actually have to have some kind of sort of intention prediction. And I'll come back to that later. But I think this is an important point that I will come back in a couple of minutes again. And I promised you to tell you a little bit about hierarchies. So this is how we do it in this architecture. So we get a bunch of stuff, visual data, acoustic data, haptic data, anything you want. Basically, there's a multidimensional states coming out of your sensors, and we feed it to this inverse models I told you about, like Gaussian processing. So basically, a bunch of inverse models. But not only in one level of hierarchy, right? So we have a bunch of models at this level, but also increasingly you're using things like grammars to have also a generation of the more high-level properties of what's going on in the system now. And this happens in all these levels. So a lot of models and lots of levels that the model is happening, it is taking place at. And all this, of course, happens also in the forward models. And we do the simulation in general constantly at multiple levels of abstractions. And depending on the task, some levels will actually do better than others, and we use them for those tasks. Let me give you examples because at this point it's been I've done about halfway my talk, so let me start giving you some videos because otherwise people get bored. So let me show you an example. So here's some work we did with Professor Choi's group from Seoul National University. So this is essentially a bunch of deep neural networks working in parallel, and we have a lot of variants with correlation filters, with autoencoders, a lot of different variants. But essentially, what I want to show you is that we don't use just one network, because one network will do well in some circumstances and some others will do in other circumstances, but we train multiple ones and then we just switch through between them based on the quality of the prediction. So for example, here you saw this in this video, I'll play it again. You have a change in both the illumination, but also the scale, and the camera is moving, and different networks might have been trained and performed better in different scenes, but here you saw a little bit here, different ones are switching, different models are doing better in different scenes, so we switch them among them very quickly. The same idea in terms of modeling is also working for if we wanted to understand how a person is moving, but we have noisy data. So this is essentially, here is the ground truth. This is what the person is actually doing, doing, I don't know what you call it, a rotation of the hands. This is, let's say, the same data, but very noisy. So you maybe have wearable sensors or camera data with a lot of occlusions, or you're wearing, clothes, something, you might not get very good data. And by having a lot of different models that are competing for explaining what's going on, we can actually reconstruct what actually is going on and get a reconstruction of this sort, which is, it is noisy, but is much better than, of course, what we had in originally, right? From 80% data missing. By the way, I will show a lot of different things, but there are papers on all these things, and I can come back to the different things if anybody's interested in a particular subpart. We use these kind of models for lower levels of the action hierarchy, right? So if I want to model a movement, a rehabilitation exercise, dance, or anything like that, we use this because they're better for dealing with noise. But if I wanted to do something a bit higher level, so for example here, an example of where you try to teach the robot, the ICAB robot, to play the Towers of Hanoi or Tower of London, whatever how. In here, the task, we don't care so much about how the user is doing this in terms of trajectories, because the trajectory doesn't matter, but we do care of how he's actually solving the problem. Now, if you're trying to do this with a neural network, you possibly can do it, but you will suffer, right? You need millions of examples, and you could do a lot of different hacks in order to make it work. So what we actually do is we're actually trying to see whether we can use stochastic context-free grammars. So this is like context-free grammars are basically grammatical structures, production rules, but we actually have probabilities associated with them based on the observation we have seen. So we actually extract from the demonstration a kind of like a task structure that then we can send it to the ICAB, and the ICAB can learn from us and imitate us, or model the way that we have done it, right? And you can see that the nice thing about this is, if for tasks like this where you have repetition or recursion, it's quite nice to have these grammatical structures, because you can do many more things that you could do with neural networks. We have found out, right? Other people might have different experience. We can also do anomaly detection if we have grammatical structures. This is some work we did with modeling multiple activities detection. This is a bunch of students cooking pancakes in the lab, the kind of fun you have like in a robotics lab, right? So in here, what you have is actually multiple people that are doing the same activity, but because in real systems, in robotic systems, you don't have infinite computational power, we actually use grammars to understand where should we reallocate the attention, because for example, in some parts of the scene, we understand what's going on, but in some other parts of the scene, we don't understand what's going on, and the grammar cannot explain it. Therefore, we have to focus and understand a bit more in what is in that part. By the way, if anybody needs a data set of multiple activities in doing pancakes, we have one of these as well, if you can download it. Okay, so I basically told you in a way that we have a bunch of different models, right? So inverse models, forward models, etc. But where do this come from, right? I mean, you need to have a model to be able to use it in a predictive manner. And what I want to show you here, let me start from the beginning again a little bit. So one of the things that we do a lot is learning, right? So we actually trying to learn these models. So on the left is the work we did with Martina a while back, where essentially she was trying to get the ICAP to learn its own model by, in a way, like developmentally, by trying to experiment. So the robot just basically randomly move its own arm and then observing and trying to associate the motor commands with the sensory consequences. So to understand how the motor commands affect different structures. And she did not only just that, but also she did a lot of work with different robots, right? We don't want to have this working with only one robot. But the idea here was actually essentially a sense of calibration, right? You're learning what are the effects of your model, of your commands on this particular system at this particular time to learn your internal models. And on the right-hand side, we can learn models, of course, of others. So here we did some work on with Hyunjin, with some work on observing humans as they move and extracting the articulations just by this movement. So on the top, the right-hand side, you understand how does this person move and what are the different articulated structures that can explain its movements just by observation. So basically, learning is a kind of a fundamental aspect in our lab. We're trying to see how far can we go by learning these models, right? Now, once I have a model of the robot itself and a model of the other people, one thing that we want to see is, can we match these, right? So can I understand how two different agents are similar to each other? So what we did, we used HyperGraph Matching, which essentially says, let me try to do some matching between different components. So for example, you see the human movement and possibly the robot movement below, and based on a bunch of criteria like how, starting from the bottom, do they move in the same way? Do they look the same? Is the structure similar? So we use a bunch of criteria and we see how the two different things correspond to each other and how does the movement of one agent correspond to another model that possibly we know more about, right? So we can extract some properties from that model. You can use this for a lot of interesting kind of like analogical reasoning aspects. So for example, you can do things like mapping a movement of your own arm to a movement of an arm of another person seen in your camera. You can see how you can do self mapping. So for example, you can see that I extracted the arm of my left arm, but you know what, my right arm is similar. Or you can, of course, if you're seeing two different agents, so a third robot sees a person and a robot, then you can actually match between the two of them. There is interesting aspects also, which I go to some other time, but also you can match things, for example, from one robot to another, my articulation, so you can understand models from between different robots, how do they relate. Here is, for example, as I said, how do you match human movement to between a human and a robot? But also you can do crazy things like this, right? If you want to explain how a crane works, you can actually basically show it analogic. You can do sort of reasoning of how does it move by your hand or your finger. And of course, as I said before, you can actually map the movement of a human to a movement of a robot to actually understand a little bit the similarities between the different agents. The similarities also are not only on the movement level, but I don't know whether you can hear the sound, but also we can actually attach a bit of linguistics in it. So we attach linguistic labels. So if you don't hear the sound,
we do hear it. It's a bit soft. I don't know whether there is any way to increase the volume.
Let me try. Yeah.
Nice. I know that I have a middle.
Move your middle.
Nice. I will do some exercise with my right arm. I will move my middle.
So essentially, what I'll switch because the sound is not great. The robot is actually moving parts of its body, doing the motor bubbly that we were telling before. But then it tells the human, what do you call this body part, right? In your language, and the person says, well, I call this the middle finger, right? And the robot says, okay, I understand that you refer to this part of the model as middle finger. Then it says to you, can you please touch it? So you touch the finger, and it gets the tactile sensing as well from the touching, so it now knows how to associate haptic, acoustic, linguistic, and visual data with its model, and is able to start discussing with the person later how you can use this language to explain its own memories, but also explain a little bit the interaction to the user. And this was a couple of projects we did called EFA and WYSI at the European level with a lot of interesting partners across the EU. Once you have, so far I've been telling you about purely on the body parts, right? But of course we know that we can understand a lot about people's intentions from where they're looking at, right? So one aspect we've been working quite a lot on is this perspective taking, which first step is to understand where do people look at, the gaze estimation. So we did quite a lot of data collection with wearable sensors, at the same time recording from a motion capture system and a bunch of cameras around to collect subjects from many different people, like 100,000 trained images, as it says there, with a very high pose and appearance variation. So we have a distance from the recording part, right? So there's a lot of eye trackers out there that work from the distance that we are now, in front of a monitor, but they wouldn't work for the situation that we want, which is a human interacting with a robot at some distance. I'll cut the story short here. Basically, it worked quite well. You guys are welcome to download code and datasets if you need an eye tracker. It's freely available for anybody to use. And the good thing about it is also you can actually do multiple human tracking, as you can see on the right. Essentially, what we want to do from this is get an idea, where is the person looking at, right? We understand their body, we understand how they move, but it would be nice to know where they're looking at as well, because that will give me a clue on the intention of what they're trying to do. And what we do then is this kind of like perspective taking, right? So this is a setup, right? So you have a robot and you have a human, and we like to know, can we understand what the person is looking at? So the robot just moves around the environment, builds a model of the environment, and understands the objects that are in this environment, right? So essentially building a map, a 3D model of the environment that is operating in. Then a human goes in front of the robot, and we're trying to do this head pose estimation. I was telling you eye gaze and head pose estimation to understand what is the direction of movement of the head of the person, the eye gaze. And from that information, now we can make a little bit of reasoning of what can this person see from their perspective, right? So if we block some things, although the robots can see them, the human cannot. And this kind of capability allows us to understand the situation from the perspective of the human, right? So if we want to say something like pick up the cap, then the robot can understand what cap the human is referring to, because maybe it cannot see both caps, right? If there are more than one. And also we can actually reconstruct the visual scene from the perspective of the human. And we have found that these kind of perspective taking techniques help us make the interaction a bit more fluid, because knowing what the person is looking at and what is their perspective helps us understand a little bit more about what is currently in their internal state in their minds, right? Now, apart from this, based on the information we have from the eye gaze, sorry, this thing is not playing. Sorry, it's not playing this one. Fine. But basically, as the human is moving in the environment, we record where this person is looking at, and we can use this information together with physiological information, eye tracking, wearable sensors, anything basically we are allowed to use with this user. We can actually try to see whether we can infer internal states. And the kind of things we want is cognitive workload, the effort, the comfort, especially on the right-hand side, as you see the way that we're going to help dressing might be comfortable or uncomfortable for certain people. And in this node we're starting now, we want to see, the trust level. Can we use wearable sensors and visual information to infer the trust levels of the person? It's a very long-term goal. It's a difficult thing to do, but this is something we would like to try to do. On a more maybe constrained environment, because we don't move that much, but nevertheless very important, we try to do cognitive load estimation for drive scenarios. So we have a racing simulator in the lab, and we try to see whether we, from eye gaze and head pose data and wearable sensors, can we actually estimate whether the person is now under heavy cognitive load or low cognitive load. In order to know the ground truth of this, we use something called the end-back task, which is, as you can see, as the person is driving, they are supposed to avoid the obstacles, but also remember the numbers that are actually shown on the screen. And we can make the task more difficult by asking them to remember not the current number, but n number back. So 1, 2, 3 numbers backwards, which actually taxes them in terms of workload. And we have shown in a couple of papers that we can actually use neural networks to estimate in real time the cognitive workload of the person as they're doing, because then we know whether to inject some help or not based on whether we think the person is actually under too much load. Taking all the techniques I showed you before and putting them together, we interested very much in how these models change over time, as I mentioned. So in one of the projects we were looking at autobiographical memories, essentially whether we can build biographies in a way, what has this person, what these interactions with this person have been in the past. And here Martina has been interacting with the iCab, and again, I don't know whether you can hear it very well. I'll stop the sound and I will just speak instead. So the robot essentially talks with a person, and when the person says, "Do you remember a certain thing?" the robot can actually retrieve the information. For example, if they were doing a rehabilitation exercise, they can show you the video of that exercise that you were doing at that time and how well you were performing. And that helps a little bit because by having a sort of a diary of how you improve over time, you can actually motivate the person even when they don't see any improvement themselves. You can tell them, although you cannot see it, here I'm analyzing your arm and I can show you that you are 1% better. You don't see it, but you actually do get better over time, right? There are a lot of aspects of, we have to work on these things, security, privacy. Of course, in this case, of course, the data never leave the robot. But if you wanted to use cloud services, there is a lot of interesting aspects to how you can actually use differential privacy or other techniques for keeping this data private in terms of interaction with the users. Okay, so I kind of did the 2/3 of my talk. I'll go now to a little bit more into the downstream, right? So all this time I was going a little bit upstream, so going from the humans to models. So here I'm basically saying, okay, let's say that I have a model, so I acquired the model with all the techniques I showed you before. How can I help? On the left-hand side, you will see the more direct approach, right? So this is a kid that never driven a wheelchair before in his life. So we put him on this wheelchair and we do some tests. Here the task is to just follow me. So as the kid is moving around, we monitor how he's doing. And here, by the way, the kid is ignoring my instructions and doing something else, as kids do. And the idea is we don't help all the time, but we adjust the control system to give assistance only when it's needed. So, for example, here, we predict with the internal models that the kids will do well. But then as the interaction progressed here, oops, the kids, we kind of predicted it's probably going to smash the robot on the wall. So we kind of intervene there and correct a little bit the assistance. This is a direct approach on the left. On the right-hand side, we see a little bit of an indirect approach, a bit more crazy project where we actually stick a kind of a humanoid robot, an assistant in front of the robot, and it actually is giving directions to the person, to the kid, of how to do the task. So the assistance is essentially through a directional aspect. And we found that actually by having a real system in front of you that does this, it actually improved quite a lot the performance of the kids, right? I will skip this. One of the aspects that we struggle quite a lot in human-robot collaboration is that if you try to help you with a robot, a human, the human might not have a good understanding of what you are trying to do, right? What is the robot trying to do? Why is the robot behaving this way? So the robot might be trying to change the control system to adapt to your needs, but because you are also changing your understanding and you're learning constantly, you might actually get a little bit of misalignment about what is your internal model of the robot and what is the robot's internal models as well. So what we have done is we try to see whether we can use augmented reality to explain this process and understand a little bit more about the internal aspects of the system. So here is for example, the Mark is moving the wheelchair around, and through the HoloLens we actually display overlay some information to explain to the user, this is what I'm thinking of, and this is how I'm going to do the next step, so the person can actually understand the intention of the robot. So the robot's trying to understand the intention of the humans, but also the other way around. And this, Rodrigo, another one of my PhD students, is actually doing the same thing now, but with multiple robots. So you have a wheelchair, but the wheelchair itself is talking to the other robots, in this case, the ABB Yumi in the environment, and the two robots can coordinate and show to the human what is possible in this environment right now, using basically displaying to the users the affordances of the environment. How can it help you? By doing this kind of augmented reality interfaces, we believe that we can increase the user acceptability and the level of trust, because essentially we're providing transparent and explainable assistance, right? So we don't just help, but we're actually telling the person how we're helping. And I think that's kind of like a bit of an overview of all the technical work. I started the discussion in the beginning by saying that our node would be very happy to collaborate with your node, either in this aspects that I discussed now on healthcare aspects and human interaction, or any other of the tasks that we are working on. And in this aspect, the hammer has been shown that this architecture plays quite well with others. So we have used this architecture as part of a component of larger systems in a multiple EU projects to do things like intention prediction and action selection. On the left-hand side, in the EFA project, we did musical interaction, real-time multimodal interaction. On the WYSIWYG project in the middle, we did autobiographical memories. And on the Alize and PAL projects on the right, it was more work on teaching kids with chronic conditions how to do their more exercises, in this case, dancing. So we'll be very happy basically to work more with people that might be interested in using this kind of techniques in their systems, and vice versa. There are a lot of other projects that I did not mention. The IPAL project is going right now on robot-based dataset construction. We have a project on closed-loop BCI control. We have a project on verification of autonomous vehicles and safety. And of course, the most of the work I did was in this personal assistive robotics part. But I guess all these things I can explain them in another talk another day. With all this, I would like to thank you very much for your attention. I think that's my 50 minutes up. To summarize, the work in my lab down at Imperial is on personal assistive robotics. We try to personalize the robot behavior, essentially to maximize the user's development and the outcomes of the task they are trying to do. For doing this, we engage a lot in generative modeling of the user skills, the preferences and intentions. So we want to not only build some classifiers, but trying to internally model what we see externally in a generative manner. And I guess the major interesting challenge that will stay for a long time in my lab, I think, is when to help and how to help, right? We shouldn't, as I said in the beginning, we shouldn't always help, but we should look a little bit into the long-term development of the person we're trying to help and make sure we take that into consideration. With that, I'll stop here. And if you guys want to see any papers or code that you want to download on datasets, the website is at the bottom left of my screen now. And most of the videos I've shown you today, if you didn't have a chance to get them well, or the quality of the transmission was not great, you can get them from there as well. So thank you very much, and I'll pass back to Mohammed for any discussion we might want to have.
Thank you very
for your
much.
attention.
Thank you very much. Very interesting talk. We have time for a few questions. Is there anyone who wants to start with the first question? Yeah, there is a hand